Hello, in this video we are going to find what is a reference frame. In the last video we have seen that motion is a combined property of observer and the object under observation. That is, it depends upon the perspective or particular point from where we are making our observation. That particular point or perspective is known as reference frame. We can represent the reference frame with a set of three mutually perpendicular axes, such that any axis is perpendicular to other two axes. This axis is known as reference axis. Here we have fixed three scales along the three axes because we need to measure the distance of a certain object along these three axes. Now, this axis is known as reference axis, x, y, and z, and this point is known as origin of axes or simply the origin. Now, why we need only three axes and not greater than three axes is because that in order to specify the position of an object like this car, in order to specify the position of the car in space, we need to measure the distance of this car from these three axes. If we add any other axis, then it will just replicate the same situation. That means it is just adding another reference frame, and we are just again measuring the distance of this car from these three axes. That is why we need only three axes in order to represent a reference frame. These three axes, sometimes we call it as dimension. So we live in a three-dimensional space. Now these three axes are physical axes because we can move forward as well as backward along these three axes. But in order to specify the position of an object in space, we need a non-physical dimension, that is time. Because maybe the car at a certain instant of time, the car is at this point of space, but at any other instant of time the car may not be here. That means the car is in motion, so it is changing its position along these three physical axes. So time is a non-physical dimension, but in any other universe or any other point of our universe, if the laws of the physics are somehow different so that we can represent time as a physical dimension, then we can move forward as well as backward in time. So time travel is possible. That is what we have seen on the movie Interstellar. So we can say reference frame is nothing but a set of three mutually perpendicular axes fixed with a clock. So we can use this reference frame for analyzing the motion of an object by denoting the change of position of the object with respect to these three axes. Now obviously that will be a three-dimensional motion.
However, we can analyze the motion of an object in less than three-dimensional space. Like for these two axes, this is a two-dimensional space, and if the car is moving such that it is changing its position with respect to these two axes, then it is like if the car is going like this, then it is changing its position with respect to both of these two axes. Then it is a two-dimensional motion. We need it during pen and paper analysis. And if the car is moving in such a way that it is changing its position with respect to one of any axis, then its motion is one-dimensional motion. Like if the car is going like this, then it is changing its position with respect to this axis only. Then it is an one-dimensional motion.
Now this motion completely depends upon the reference frame. Actually, things look different at different circumstances depending upon this reference frame. And it will be much more critical when there is a relative velocity between the reference frame. Sometimes it creates a pseudo force which is very hard to explain and feel from another reference frame. Like what you are seeing right now is I am moving in this direction. But if you look carefully, it is not me, but my background is actually moving. But we are habituated to think that one is fixed, and you cannot even tell if a body is moving uniformly without any acceleration by conducting any physical experiment, maybe it is electromagnetic in nature, because all the laws of physics, including the electromagnetic one, appears the same when in static condition as well as when the body is moving uniformly.
Like as we can see here, if we throw a ball vertically up while standing on the ground, the ball will come to our hand. But if we do the same thing while on a train moving with uniform velocity, the ball will still come to our hand.
And we can find it with an experiment also. Here we have a cart throwing ball while moving uniformly in forward direction. And you will find that every time the ball will return to the cart. And if you look specifically, you will find that the ball is moving in a parabolic path. And that is because we are seeing the motion of the ball from the earth reference frame. But someone who is sitting on the truck will find only the vertically up and down motion of the ball, because the ball is moving with him with the same velocity. The same thing will happen if we roll down the cart in an inclined plane. Later, during the analysis of force, we will resolve the force and find that the horizontal component of the force is responsible for the horizontal movement of the ball, and both with the vertical force due to which the ball is moving vertically up and the horizontal force due to the movement of the cart, the resultant motion of the ball, that means the resultant force acting on the ball, will be such that it forces the ball to move in a parabolic path. We are going to find the same thing. I have a ball, and if I throw the ball upward, then it will going to come to my hand. But if I do the same thing while standing on the escalator, the ball will still come to my hand and the motion of the ball will still appear vertically up and down to me. But someone who is standing there on the stair and filming the ball, the motion of the ball will completely look different to him. Here we can find that although I am moving with the escalator, the ball always comes to my hand. This is because due to the horizontal component of force that is exerted by me while throwing the ball. Due to it, the ball is traveling with same velocity with me. Same thing will happen while going down through the escalator. Here, while seeing from the same reference frame, we can only observe the vertical motion of the ball. Here we can find that although the train is moving uniformly, but there is no effect of it on the pendulum's motion. We can still determine its time period with the same formula, t is equal to 2 pi under root of L by g. So practically there is no effect of uniform's motion on the laws of physics. It holds as like when we are in rest. Here we can find that I am rotating a ball while moving, but as the camera is fixed with my reference frame, the motion of the ball is completely circular. But when the same thing is viewed from the earth reference frame, its motion looks completely different, and that kind of motion is known as cycloid. We can see it from the animation. So motion of the body will appear completely different depending upon the point from where it is being observed. So the study of the motion solely depends upon the reference frame from where we are conducting our experiment.